Let's consider this another item. We have the number of ways to distribute 40 identical balls to 7 distinct boxes if box 1 must hold at least 3 and at most 10 of the balls. We only have one restriction. That's for our box 1. Let's try to solve this using ordinary geometric functions and identify again. You have here a sub r, x to the power of r. You're going to solve for a sub r, the number of ways of distributing or selecting r objects in this manner using ordinary geometric functions. That would mean we're going to solve for the number of ways to distribute 40 identical balls and identify the coefficient for that using again the ordinary generating functions. So how do we write this in that manner? Now, take note that in this situation here, that number of ways to distribute 40 identical balls to 7 distinct boxes. So for box 1, okay? So for box 1, there is a restriction that it should all hold at least 3 and at most 10. So in form, you can actually get here 3 until 10. That would mean its generating function will remove the possibility of selecting 1, 2, even the none, and then 11 up. That would mean its generating function is should be identified as x cubed plus x to the power of 4 plus x to the power of 5 plus x to the power of 6 plus x to the power of 7 plus x to the power of 8, 9 until 10 only. That's for our box 1. But for box 2 to box 6, it's actually unrestricted. So we'll have actually the 1 plus x squared plus that so on and so forth. And there are 5 of them. You have box 2, 3, 4, 5, 6. We will have this form here. Okay. So what we need to do is to multiply all of this and get the x to the power of 40. And again, whatever would be its coefficient, that's the answer to the item. Let's try to simplify them one by one. For box 1, we have here this form. So if I'm going to factor x cubed, okay, on this given expression, sorry for that, x cubed, what remains on our first term is just 1. For second term is x. Third term is x squared, x to the power of 3, x to the power of 4, plus, sorry, that's 7, right? For 8, x to the power of 5, plus 9, 6, and for 10, x to the power of 7. I'm writing this one because this can be simplified still in another form using the formula for the finite geometric series. The finite geometric series tells us the sum of a finite geometric series using the common ratio, because if you have the common ratio, as we move from one term to the other, the common ratio is x. The sum is actually given as 1 minus r to the power of n over 1 minus r, or r to the n minus 1 over r minus 1. We'll be using this form so that we can actually pattern it to the form of this later. So with that, our r is x. It's actually 1 minus x to the power. Our n is 1, 2, 3, 4, 5, 6, 7, 8. X to the power of 8 over 1 minus x. So this is actually written as here x cubed times 1 minus x to the power of 8 over 1 minus x to represent that string. Now notice that then again, by the way, I have made an incorrect answer here. Actually, there are 7 distinct boxes. There's actually 7, so that's 6 here. Sorry for that, pardon for that. But again, this will be multiplied. This form will be multiplied here back. And we know that in that form, if we have going for this one here, 1 plus x squared, there's no restriction. This will be equivalent to 1 over 1 minus x. And since there are 6 of them, that's equivalent to this form. That is why the next part here is x cubed, 1 minus x to the power of 8, 1 minus x times 1 over 1 minus x raised to the power of 6. Again, we're going to look here for x to the power of 40, and again, its coefficient is the answer to the item. So how do we do this? Simplify them step by step. So they have here x cubed, you will have here times 1 minus x to the power of 8, sorry for that, over 1 minus x. And this one here is actually 1 minus x to the power of negative 6. Okay? Using the negative law of exponents. But still, we have 1 minus x here, so you can actually combine that. You will have here x cubed times 1 minus x to the power of 8. Then you have here 1 minus x, now negative 7, because the 1 minus x is a denominator. And with this now, we can use the version of 1 minus x to the power of negative n, which could be expanded in this form: 1 plus n minus 1, combination 1. That's for x, right? And you have here plus 2 plus n minus x, combination 2, for our x squared, until you reach your rth term of r plus n minus 1, combination r, x to the power of r. We need to solve the general form in rth term so that we can actually solve for x to the power of 40 later on. In short, this for the rth term can be transformed to this form. Okay, so this would be equivalent in rth term, x cubed 1 minus x to the power of 8, and instead of this form, we'll be writing r plus n minus 1, combination r, for your x to the power of r for our rth term. And our r later on will be changed to a certain number which would match 40. So with that, simply multiply this 2. You will have x to the power of 3 minus x to the power of 11, right? By multiplication. And again, this is to be multiplied by r plus n minus 1, combination r, x to the power of r. This will be multiplied here. So further, you will have here the result of x to the power of 3 plus r, okay? Using the multiplication law of exponents, meaning adding exponents, then times r plus n minus 1, combination r, okay? And then you have minus x to the power of 11 plus r times r plus n minus 1, combination r. Now, this is the rth term. Take note, our goal is x to the power of 40, and whatever be the coefficient, that's the result to our item of distributing 40 identical balls to 7 boxes where one of the box has a condition. Now for this, let's try to make this x to the power of 40. When this is possible, that is only possible if r there in the first term is actually 37. That's actually x to the power of 3 plus 37, right? In short, our r is 37 plus our n, which is 7 objects, okay? 7 boxes rather, minus 1, combination 37. For our second term, it should not be 37 because this should match 40 as well. So what we need here is actually 29. So you have x to the power of 11 plus 29. Our r is 29 now. 29 plus 7 again, minus 1, combination 29. So by factoring this again, will be x to the power of 40 and x to the power of 40. You will have 37 plus 7 minus 1, combination 37, minus, you will have 29 plus 7 minus 1, combination 29. This will be multiplied to x to the power of 40. Hence, the result for this is the item we're looking for. So simply simplify that. That's actually equal to 37 plus 7 minus 1. That's 43, combination 37, minus, again, that's multiplied by x to the power of 10, minus 29 plus 7 minus 1, combination, that's 35, combination 29. That's very large. Okay, that's very large, right? This is already okay if you're going to answer in combinatorial form, or you can even simplify it further if you would like to, but I think it's very large. 43 combination 37 minus 35 combination 29. Yes, it's very large, but if you would like the exact value, it's actually 4,473,294 for x to the, sorry, this is x to the power of 40, my bad. For x to the power of 40, and this means the number of ways to distribute 40 identical candies, balls. It's already in balls. 40 identical balls to 7 boxes, where there is a restriction for box 1 that it should hold at least 3 and at most 10 of the balls. So again, the answer here is 4,473,294. Thank you very much for watching.